Hey everyone, today we are pulling back the curtain on the invisible system that basically secures our entire digital lives. It's called Public Key Infrastructure, or PKI for short, and it's the silent guardian behind your banking, your shopping, everything. So let's dive in and see how it all works.
We've all seen it, right? A million times. That little padlock icon up in the address bar of your browser. It makes us feel safe, sure, but what is actually going on behind the scenes to make that lock appear? What does it truly represent? Well, that's exactly what we're going to unpack today. The short answer? That padlock represents a massive system of trust. It's a huge global framework that's working silently in the background every single time you connect to a secure website. And that framework has a name: Public Key Infrastructure. Okay, so what is PKI really? You can think of it as the system that manages our digital identities online, and it has two absolutely critical jobs. First, confidentiality, which is just a fancy way of saying it keeps your data private. And second, integrity, which is all about proving you're talking to who you think you're talking to and not some imposter. Now, to really appreciate why PKI is so brilliant, we first need to understand the problem it was built to solve. It's a fundamental puzzle that stumped early attempts at digital security, and it's called the secret key problem.
So the old way of doing things was called symmetric encryption. It's actually super simple to wrap your head around. You've got one secret key, you use that key to lock up or encrypt your message, and the person at the other end uses that exact same key to unlock it. Easy, right? Well, yeah, but it has one giant glaring weakness.
And here it is, the big problem. How in the world do you securely get that secret key to the other person? I mean, if you just send it over the internet, a bad guy could just grab it. And if they have the key, they can read every message you ever send. This was a huge roadblock for secure communication.
The solution that completely changed the game is called asymmetric encryption, and the core idea is simple but revolutionary. Instead of one shared key, everybody gets their own unique pair of keys, one that's public and one that's private. And this elegant little system solves that key exchange problem completely.
So here's how it works. Let's say Batman and Robin each create their own key pairs. Now, they can shout their public keys from the rooftops. It doesn't matter who has them. When Batman wants to send a secret message, he locks it using Robin's public key. And here's the magic trick. Once that message is locked, it can only be unlocked by Robin's corresponding private key. Not even Batman, who locked it, can open it again. Pretty cool, right?
Fantastic. So this asymmetric encryption thing solves the privacy problem. But that's only half the battle. How does Batman really know that the public key he has actually belongs to Robin? What's to stop the Joker from just sending Batman his public key and pretending to be Robin? We need a way to verify identity.
And this is where the digital certificate comes in. Honestly, the best way to think of it is as a digital passport. It's an official document that links an identity, like a website address, to a specific public key. And, just like a real passport, it's stamped, or digitally signed, by a trusted authority to prove it's the real deal.
So who is this trusted authority? It's called a certificate authority, or CA for short. Their entire job is to verify that a website owner is who they say they are before issuing them one of these digital passports. They are, for all intents and purposes, the passport offices of the internet. Now, not all CAs are created equal. There's a whole hierarchy. At the very top of the pyramid are the root CAs. Their certificates are the absolute bedrock of trust for the entire system, and they come pre-installed in your browser. Their private keys are so valuable they are literally kept in physical vaults, completely offline. These root CAs then authorize intermediate CAs to issue certificates out in the wild. And this whole process creates something called a chain of trust. It's brilliant, really. When you visit a website, your browser looks at its certificate and sees it was signed by an intermediate CA. Then it checks if that CA certificate was signed by a root CA it already trusts. And because the chain is unbroken, voila, your browser trusts the website, and you get that little padlock. Okay, this system is incredibly powerful. But what happens if a certificate needs to be canceled? Maybe a company's private key gets stolen, or they just go out of business. That digital passport needs to be revoked before it expires. How does that work?
There are two main ways this happens. The old school method is a certificate revocation list, or CRL. Think of it like a most wanted poster of bad certificates that your browser downloads every so often. The catch? It can be out of date. The modern way is called OCSP. This is where your browser makes a quick, real-time call to the CA and just asks, hey, is this certificate still good? It's much faster, but it also creates a lot more traffic. The stakes in this game are incredibly high, and nothing makes that clearer than a real-world story. Back in 2011, a Dutch certificate authority called DigiNotar got hacked, and the attackers got the keys to the kingdom, the power to create new, fraudulent certificates for any website they wanted.
And what did they do with that power? They created a fraudulent certificate for Google. And this was reportedly used to intercept the secure Gmail traffic of, get this, more than 300,000 people, mostly in Iran. They were literally tricking people's browsers into thinking a fake site was the real Google and then reading their private emails.
The fallout was swift and absolute. As soon as the breach was made public, every major browser developer pushed out an emergency update that just deleted DigiNotar from their trusted lists. Instantly, every certificate they had ever issued became completely worthless. The company went bankrupt in a matter of weeks. It's a chilling reminder. In the world of PKI, trust is everything. Once it's gone, you have nothing.
So let's peek under the hood for a second. Every single one of these certificates follows a standard format. And in the blink of an eye, your browser scans this data. It checks the issuer. Who signed this thing? It checks the validity period. Is it still good or has it expired? And, most importantly, it checks the subject. Is this certificate actually for the website I'm trying to go to? Okay, so after all of that, after the keys and the certificates and the chains of trust, let's bring it all back home. Why does this complex, totally invisible system actually matter to you in your day-to-day life?
Well, the simple answer is that PKI is the bedrock of our digital trust. It's the technology that lets you confidently type your credit card number into a shopping site. It's what keeps your online banking sessions secure from spies. It's what verifies that the software update you're about to install is really from Microsoft or Apple and not some hacker. It is constantly, silently protecting you. But here's the crucial takeaway. This entire global web of trust, this system securing trillions of dollars in our most intimate data, it all hinges on one single, simple assumption, that private keys are kept private. And as the DigiNotar disaster showed us, that trust can be shattered. So the final question isn't just if that foundation can be shaken again, but in a world of ever-evolving threats, just how permanent is that trust really?